Very excited there. Group B. Go ahead, Group B. Group B.
I think we can start waiting for our leader to show the slide.
Yes. Very good. Huang Xuesheng. Here we go. You guys use Canva. Very nice. Maybe we start from, okay. Oh, yeah, very nice drawing. Yeah.
So we are Group B, and let's start from our test 1. Okay. Next page, you can go to task 1. Yeah. Next page. So next page, thanks. And so this chart illustrates how 3 distinct architectures scale as a total neuron budget increase from 1,000 to 3,000. And so we can first see the blue line here. The white network maintains the highest validation accuracy across the entire spectrum of K. Yeah.
Can I ask how many average did you do here? How many runs did you average this over?
I only run about 2 times because this takes much time, I think. Yeah, that total 1,000 to 3,000. So I have to do some for like different structure for only K equals to 1,000. I'll say later. Yeah. So yeah, I think it proved to be the most efficient for this specific classification task. So it shows that the flat curve is maybe it is because there is too much neuron in a layer for the small test like this. And then we're
sorry, how many iterations here? This is what is the number of iterations that you fix? The number of iterations.
I think it's 6,000.
Okay. And the batch size, 128. What's the batch size?
It's about 2,000 like that.
The batch size is 2,000. Okay.
Yeah.
Go ahead. Add this information to the slide, please. Go ahead.
Yeah. Okay. So you'll see the deep architecture start with the lowest accuracy at about 1,000, and I think it demonstrates the most consistent upward trends as the budget scales. This might suggest that the deep network requires a much larger absolute number of neurons to function effectively compared to swallow networks.
Can I tell you something? Let me tell you something. So here you clearly overtrain the network, right? Meaning that you reach an accuracy of 98%, right? 97.6, 98%. So in a sense, the plot that we have is 3-dimensional, right? On let's say on the z-axis we have t, the number of iterations. On the y-axis we have the accuracy, and on the x-axis we have the number of nodes. In my mind, you pushed the performance over the t to be very, very far out, right? So because your t is so large, and so the difference between the networks it's a little bit less noticeable, right? Because you train the network for so long. What we also want to know is, let's say, for some t which is smaller, let's say t equal to 100, because we also want to see, for example, how fast the network learns, right? So you also need to
Yeah. So maybe the K will be lower like that.
Correct. Because right now everything is at 98, right? So in a sense,
yeah. So maybe I have to try that. Maybe K 100 to 1,000 like that.
Correct. Usually we call it T. You want to call it K? It doesn't matter.
Okay.
Number of iterations. Doesn't matter. Go ahead.
Okay, so the next page. Oh, and we see the bottleneck architecture shows a little bit higher than the deep model. That's for the last page, yeah. So, and then I set A equals to 1,000 and create 6 kind of structure with different layers and neuron ratio like these shows here. Okay, so next page. So we show the output here by and we can see there's the clear inverse relationship between the network depth and the performance. And yeah, I have shown the level numbers on the bottom. So the wide architecture as a single layer achieves the highest mean accuracy, and the 2-layer is a close second, and the 5-layer deep one performs the worst. So I think the reason is like we have multiplication between both layers, and the signal might be multiplied many times in the process of transmission, and might causing the signal to be weaker and weaker like that.
I don't think this is it. I think it's because the learning problem is so simple. Okay.
Oh yeah, there's might be like another. I think that there's another reason, maybe like that.
Because the network having 5 layers is nothing, right? I mean, if you look at some modern architecture, they have thousands of layers, right? So
yeah,
so
the task is too easy for this structure like that.
Yeah, so you get the numerical instability when your number of layers is the order of thousands, right? If you if it's 5, it's not numerical instability. It's due to the learning problem. Yeah. So there is a match between the learning problem and the architecture, right? And as you practice more and more this, you'll realize. Go ahead.
Okay, so the other thing we can solve like the bottleneck penalty is like architecture that force information through narrow layers will lead to performance drops, like or glass here, the fourth one and the third one funnel. We can see the total neurons and levels are the same, but switching data through several bottlenecks likely result information loss. So the funnel will be a slightly higher accuracy like that.
Yeah. Also, there is a little bit debatable. It's a little bit debatable. Yeah. Because so the bottleneck architecture, you use it when you have a very high dimensional image. You have a high dimensional input and you want to condense the information into a small set of variables. So again, it's if the image was more complex, then the bottleneck would be more useful. It's just that
so it's also because the task is
I think
simple.
so, because if you think about the MNIST, right? So the image it's very large, but it's mostly zeros, right? So the image is mostly zeros because it's only like a small trace that is non-zero element, right? So the dimension of the input, it is very small. So the bottleneck cannot lose too much information because the image is so little information. So yeah. I will agree with you in some other domain. Like if the input was less sparse, I will agree with you. In this case, I think it's debatable. Go ahead.
Right. So unless we saw the performance gap between the best, the wide, and the worst for the deep one, and is significant. So this might prove that specific tasks for neural network, how the neurons are arranged, and matters heavily. Like that. Okay, so next.
So task 2, where we investigated how data augmentation improves generalization in deep neural network. First of all, we choose the best architecture we acquired from text 1, that is wide. To start, We established a baseline model without any data augmentation. As you can see from our data, the baseline achieved a very high training accuracy of roughly 99.53%, but the validation accuracy was only 97.78%. This noticeable gap indicates that our baseline model was overfitting. It was memorizing the training data but struggling to generalize to unseen images. To address this, we applied 5 different augmentation strategies: rotation, translation, scaling, random erasing, and a combination of rotation plus translation. Last page was our bar chart, and this is our table. We can answer a few key questions about their performance. First, which augmentation gave the largest improvement? That would be rotation. It achieved the highest validation accuracy at 98.25%, giving us a solid 0.0046 boost over the baseline.
I mean, your language, it's a little bit funny for me because the accuracy is still 98%. So it's still a very, very accuracy. And then you say solid 0.000046. It's a little bit funny, okay? So just
yes,
it's a little bit funny.
Because as handwritten digits naturally vary in their tilts. Secondly, did any augmentation hurt performance? In our simulation, no every single method we tested yield a positive for over the baseline, with random erasing bringing the smallest, yet it's still positive. Third, the combination outperformed single augmentations. Interestingly, in our experiment, the answer is no. Our combination of rotation and translation reached 98.18%. While this is excellent result, it's still lower than using rotation alone. This suggests that applying too many transformations might distort the digits too much, making them harder for the network to learn efficiently. Finally, we want to answer the most important question. Does augmentation actually reduce overfitting? To prove this, we plotted a learning curves for all our experiments in this 2x3 grid. If you look at the baseline plot on the top left, you can clearly see the blue line, the training accuracy, shooting up toward 1.0, while the orange validation line stays flat at the bottom. That wide gap is the visual definition of overfitting. However, if you look at other 5 plots where augmentation was applied, the behavior completely changes. Because the training images are constantly being altered, the blue training line is pulled down. The test is harder now, but as the result, the orange validation line moves up and closely tracks to the blue line. The gap between training and validation has practically disappeared. In conclusion, our experiments clearly demonstrate that data augmentation is a highly effective regulation technique. By forcing the model to learn invariant features rather than memorizing exact pixels, we successfully reduce overfitting and improve overall generalization.
So it's a regularization. It's not. So it's a regularization technique. Okay, just a vocabulary. Very good. Very nice. Very nice.
In Tech 3, we analyze the model beyond overall accuracy by looking at each digit separately. First, we use per class accuracy and confusion metrics to identify difficult digits. Then, we reduce the training data of one digit to study the effect of imbalance.
Let me ask you a question. Which numbers do you think are the hardest to classify before we see the results? In your mind, which numbers are the harder to classify?
Maybe 8.
8 versus 8? You confuse 8 with what?
What?
So if you had to if you had to write, right, and you see somebody write an 8, you will confuse the 8 with which other number?
Maybe 3 or 9.
And then 1 and 7, I think, right?
Yeah.
And then the issue is that 4, we have many different ways of writing. The white people in the West, we have many different ways of writing the 4. Also, the 7, sometimes we put the dash, sometimes we don't put the dash. Yeah, because in the West, we don't have stroke orders when we write, right? So everybody has their own tradition of how they write numbers. So, okay, go ahead.
Next page. From the per class accuracy, we can see that the overall accuracy is very high. However, the performance is not uniform across all digits. Digit 8 has the lowest accuracy, around 0.94, making it the most difficult class. This suggests that some digits are inherently harder due to their more complex shapes. And next page. The confusion matrix gives more detailed information about the errors. Most predictions are correct, as shown on the diagonal. However, the errors are not random. The model mainly confuses visually similar digits. For example, digit 8 is often confused with 3 or 9.
Yeah. Very nice.
Next page. In this experiment, we reduce the training data of digit 8 from 100% to 10%. We retrain the model and evaluate the performance. We observe that most digits remain stable, while only digit 8 shows a noticeable decrease. This means the model is still strong overall, but it loses its ability to represent the underrepresented class. Next page.
I mean, it's still above, even with 10% of 8, you still achieve 90%, right? Nice.
100%, 15%, 20%, and 10%.
Yeah. So, but with 10%, you still have like above 90% accuracy, right? For 8, correct?
Yeah.
Yeah. So next time, just cut the y-axis. Okay. The next time, just show between, let's say, 0, 9, and 1. Otherwise, there is too much white width. I cannot see the difference between the accuracy.
Okay.
Really, you still achieve, even with 10% of 8, you still achieve such higher accuracy. Interesting. And this is the wide network, right? This is the full wide network. Oh, interesting. Okay, go ahead.
This figure shows the accuracy of digit under different data ratios. We can clearly see that the accuracy decreases as the training data decreases. The drop becomes more significant when the data is reduced to 10%. This shows that digit is a data-hungry class. And in conclusion, model performance is not uniform across all classes. Some digits, like digit 8, are more difficult and require more data. When class imbalance is introduced, the affected class drops significantly, while others remain stable. Therefore, overall accuracy is not sufficient, and per class analysis is necessary.
Can I ask you something? Because when you said something, you said that 8 is data hungry. It's kind of funny, right? 8 is. You get the joke?
Yeah.
You know that there is the joke, right? Why 5 is afraid of 7 because 7, 8, 9. You know that joke for kids. Go ahead.
Next page.
Okay. Good afternoon, everyone. I hope you're doing well. Today I'm going to present you task number 4. So in this task, we investigate whether a neural network can learn a meaningful representation of the MNIST digit using pairwise supervision. And that is without ever being told like what are the labels during the training. So instead, we train a Siamese network that only knows whether two images belong to the same class or different class.
So yeah, I hope you explained this task well, because I was trying to, it's kind of a different way of using neural networks. I hope I explained it well. This is like something that people started doing maybe 3-4 years ago. So maybe I'll interrupt you more than usual, because I think it's a very nice, I hope I was clear and explained. Go ahead.
Yeah, it's an interesting topic. So yeah, let's go to next slide. Here is just like a little overview of the methodology and approach we did. I will not go in detail, but we usually create the image, then we train it with the network, then we use the contrastive loss, which is the function, and that is distance based, and then we supervise only with batch and match and non-match. And then we evaluate via clustering. So I will go more in detail in the next slide. So let's go to the next slide. So this is network infrastructure. Here we use our, I don't know if you want us more to focus on the result, or you also curious about.
You do what
Okay.
presentation.
Okay. So this I'll just use as overview of our embedding network. So we use image that are 28 by 28 pixel that went through 2 layers of network, one that is 258 and then 122. And the output was to give dimensional of 2. So we wanted to go through those network layer to have output of 2. And we use that function for the loss function. So it's to matching the pair, where if it's equal to 1, we want to minimize like the distance, and if it's like equal to 0, we want that the distance is a large open margin. So yeah, let's then go to results. So let's go on next page. This is our training results. So here you can see the training loss over the epochs. So what we can clearly see is that we got a smooth and consistent decrease in loss. So that's what we want. That means that our network is learning efficiently. So yeah, the key point and observation here is that we see stable convergence. We see no sign of overfitting, so because it's a smooth decrease, and we see consistent improvement through training. So at each epoch we have less and less loss. So yeah, let's now visualize what the network learned in the next page. So here what we can see is a map, that two-dimensional map that spaced our training network. So for reminder, our network was never told like this is 0 or this is 9. It didn't have a label. So we just use pairs and learn whatever they match to it. So they create some labels by itself, that network. So we can look what emerged here. We see distinct, well-separated cluster, and each cluster corresponds to a different class. So we see spontaneous organization of the data, and this is purely by learning on similarity. So we can also notice how tight some of the cluster are. So digits that have a consistent and distinctive shape like 0 and 1, we can really see that they create really tight and connect groups. And other numbers that are more similar, like for example 5 and 6, we see that there's more disparity. So yeah, and we notice that there's some point that overlap, and this is not failure of the algorithm of the network. It's more a realistic reflection of the problem. So like our teacher was saying, sometime we write differently the 4, or sometime with the handwriting we can be confused if it's 3 or 8. So this is normal to have such overlapping. So okay, we can go next slide. So yeah, this is our result. So we have 93.6 clustering accuracy. So what this number represent, it's mean that we applied the key mean clustering, which is a completely unsupervised algorithm to learn about the embedding, and we got 90.3.6 digits that were assigned to this cluster that represent the true class. So yeah, this is a good performance, I would say, because we didn't, the cost for that training was almost nothing. We didn't have any labels, and as we see before with the other label, the result was 98, 99 accuracy, but still 93 is a good result for a drastical less supervision. And
do you know what is the performance if you just use clustering without, you know what I mean? If you do k-means clustering, what is the performance? Like if you do k-means, go ahead. You understand the question?
98 to 99% accuracy just by using clustering.
If you do k-means clustering on the
yes?
original data, what is the accuracy there?
I'm not sure. I think
somebody in class should know because we did it. Can somebody write in chat what is the accuracy? Because there are some people that are taking my numerical analysis class. In the numerical analysis class, they did the cluster of k-means using only. So somebody will tell. Can somebody in chat write what is the accuracy that you got? It's much lower. It's much lower. Yeah. I see somebody. Yeah, somebody is gonna write. But yeah, you can try it much lower. Just put it in the report so you can show how much you gain. Yeah.
Okay, sure.
Yeah.
And
okay,
next slides. These are questions we got. So I answered through my presentation. So can network recover a useful structure from pairwise information only? Yeah, as we see before, with 93.6% clustering accuracy, we can still recover some good information. For next question, do sample from the same digit form compact group in the learned space? Yeah, as we see in the 2D embedding visualization, we see tight clusters, and that most digits with similar that are different will create really tight cluster. And yes, the other question, which digits are easiest or hardest to separate in the embedding? 0 and 1 are the easiest, and other number like 4, 9, 3, 8 are hardest. And finally, the last question, does the clustering recover the original task? So yes, it's achieved at 93.6 accuracy, and the representation preserve enough information to nearly reconstruct the original 10 class classification task. So yeah, that's it for my part.
Yeah, so do this for me. Add
Yes.
the performance k-means without with straight up. Then
Okay.
stay on the slide. Stay on the slide there. Then you add the confusion matrix, right? Because you want to see if the confusion. So you have this confusion matrix, right? You have the confusion matrix of k-means only, embedding plus k-means, and you have the neural network only, right? And you will be able to compare the type of mistakes that you do. For example, what you will see is that the k-means will confuse the one, the slanted one and the straight one, okay? Because k-means uses the L2 distance between the images, right? So if you write a 1 which is slanted, the slanted one looks much more like a 7, right?
Mm-hmm.
And so you will see that I think you will be able to understand better how the geometry of the embedding works, because the embedding imposes a geometry on the embedding space, which is invariant to this type of rotation of the digits, right? So that's high level what I think you can do with the confusion matrix. Okay, very good.
Okay, thank you.
Any other question, guys? Yeah. Okay, very good. Okay, so group, should we do group C, guys? Can group C or group B talk to me?
I'm the leader of Group C.
Okay. Can you let me take a cup of coffee and then we start?
Okay, I'm sure.
Thank you, thank you, thank you. I need coffee to be as alert as possible, you know. Go ahead. I'm sorry for my poor jokes. Okay, it's a condition that I cannot seem to resolve. Go ahead. Group C, go ahead.
Well, I think I have problem of sharing my. I'll try it again.
Maybe you have to allow something. Or, yeah, you tell me.
I think I can, right now I can fix the problem. It's near anyone. Any other one can help me can help sharing the PowerPoint. Thank you.
Okay, this is good.
Yeah. We had two people presenting, but yeah, let's just focus on one. Yeah.
Yep, so we are Group C, and we're going to talk about Challenge 1. So first, we're going to talk about the preliminary setup. So we first established a standard training pipeline. So for data, we use the MNIST data set and loaded it using PyTorch. And we then wait, okay. So we split the data into 3 parts: the training sets, validation sets, and test sets. And for pre-processing, each image is flattened into a 784 dimensional vector and normalize the pixel values to a range between 0 and 1. And for the training setup, we use a simple and consistent configuration across all experiments. Like specifically, we use cross-entropy loss for classification and the Adam optimizer with a learning rate of 1 × 10⁻³
So you use that. So there are 2 people presenting. Can the person that is still at slide 0 stop presenting? Otherwise, we make a mess.
Oh, okay. I'm sorry.
So there is somebody is at slide 1 and somebody is at slide 3. Can the person at slide 1 stop presenting? Okay. No, you click down. Exactly. Very good. Very good. Stop presentation. No. Just stop presentation. Go back. No. Stop presentation. Exactly. Very good. Okay, go ahead.
Yeah. So we also set the batch size to 512 and trained the model for 15 epochs. And also to ensure
15 epochs. Okay.
Yeah,
good.
50. And to ensure reproducibility, we fixed the redundancies for NumPy, PyTorch, and CUDA.
Very good. This is something that I wrote in the presentation. Remember always to do this, guys, because if you don't fix the seed, you repeat your experiments and everybody gets different numbers, and then it's difficult to talk about stuff when there is randomness in the seed. Go ahead.
Okay, so in task 1, we study how the structure of the neural network affects performance under a fixed neuron budget. So instead of increasing the parameters arbitrarily, we constrain the total number of neurons and compare different architectures. So we define a neuron budget K, which represents a total number of neurons across all hidden layers. And here we have 3 different architectures. First is like wide, 1 layers with large wide, and deep one with 5 layers and small width, and bottleneck like 4 layers and alternating wide and narrows. And here are some of the results. As you can see, like the first figure shows the average validation accuracy versus the neuron budgets. And you can see that as the budget increases, all 3 architecture families improve overall. And we observed that when the neuron budget increases to around 3,000, the performance does not continue to improve, and in some cases even slightly decrease. So maybe this can be explained by diminishing returns. You can see that here in 3,000 is slightly decrease. So since MNIST is a relatively simple data set, the model already has sufficient capacity at smaller budgets. So maybe adding more neurons does not significantly improve performance.
So how many runs did you have here? It seems that you have maybe 10 runs. How
yeah,
many
10 rounds and have 15 epochs. Yep.
See, guys, after so many years working on the MNIST dataset, I can tell you how many runs you use for averaging. Go ahead.
So on the next figure, you can it shows the maximum validation accuracy for each architecture family. So compared with the average accuracy plots, you can see that the overall rankings are still the same. Wide performs the best, bottlenecks are second, and the deep is the lowest. So the wide architecture reaches the highest peak accuracy across almost all budgets. And down here, you can see the standard deviation to average validation accuracy. So it allows us to examine both performance and stability. So we can see that the wide architecture not only has the highest mean accuracy, but also relatively small error bars. So this indicates that it is more stable across different random initializations. But in contrast, like the deep architecture here has lower accuracy and generally larger variance, which suggests that maybe it's hard to train consistently. Okay, so here's some of my questions. Like, according to my knowledge, it's supposed that deep networks are generally considered more powerful than wide networks, but our results have shown the wide networks performs better on MNIST under fixed neuron budgets. So I think that one possible explanation is that MNIST is a relatively simple data. Like the images are grayscale centered and have very low variability compared to real world data sets. Like in addition, the background is almost always black and the digits are clearly separated. So the classification task does not require very complex hierarchical feature extractions. So like you said, like maybe if K equals 100 or maybe lower, then it will have a big difference. Yep. Okay.
Okay. And we're now moving to text 2, focus on the use of augmentation. Next page. Before applying augmentation, these are the parameters of the best performing module from task 1. And we use a Y module family with K equals 2,600, a batch size of 256, and was trained for 15 epochs. This baseline module achieved an average validation accuracy of 98.15%. Next page. For our experiment on augmentation, we implemented all the 6 different functions. This included common image transformations like rotation up to 15 degrees, as well as 10% translation and scaling. We also tested elastic distortion, random erasing, and adding Gaussian noise.
Next time, can you put like a color with more saturation for the for the font? Otherwise, I'm struggling to see how you write. Yeah, go ahead.
Oh, I'm sorry.
So I must put my head in the computer. Go ahead. Go ahead. Of course, I'm joking. Go ahead.
Okay. Next page. These are the data after we apply augmentations.
Wow.
As you can see, some of them are just totally destroyed, like the first and the second one.
Wow.
Next page. This is the average validation accuracy result after training. The most obvious part is that half of the combinations get poor accuracy at about 20%. This means the machine is just guessing which number is it. After we take a look, we found that the combinations with poor accuracy has one in common. they all has elastic distortion. It makes sense because you can see in the previous data, the picture after elastic distortion can barely recognize. That's why we will remove them from our data later.
But I think it's because you tuned it like to have too much of a wide range, right? So I think you allowed it to have, you know, too much distortion, right? Maybe you should have just allowed like 5% or 3%.
Yes.
Go ahead.
And this is the rest of the data after we remove elastic distortion. And because we remove some data, and I'm trying to set higher epoch now. I use
of course
equals 30 here to improve performance. Next page. So in this bar chart, we found that all transforms combinations has the lowest accuracy. So we think that multiple combinations that contains 3 or above transforms argumentation will lower the performance. So we take that out later. And next page. We also conclude the accuracy values from our last run into this table. Then looking at the accuracy values on the slide, we can observe that using no augmentation actually resulted in the best overall performance.
Really? There's something weird here. So this is validation accuracy on the non-transformed images, right? So when you do validation, when you do testing, right? Do you apply the augmentation on the testing data as well or not?
No.
So why do you have any advantage from augmentation? That's very weird.
I'm not sure. I just apply the transforms to the training data.
I think maybe you should try to tune it better, right? Because I'll tell you just very simply, right? So you know that the one, right? The one can rotate when you read the one changes angle a lot, and the 7 changes angle a lot. So if you teach the network that the one can have different rotation, you can only increase your accuracy, you know. So it's kind of strange that you don't have any advantage in the augmentation. I think try to go back to your code and try to maybe try to exploit a little bit. I think if you tune it better, you're gonna have an advantage because that's what you expect, right? So it's so there's something strange here. Go ahead.
Okay. The runs without augmentations has a larger standard deviation also. It means the module's performance was less stable across multiple runs. Okay,
I think
next page.
it's a tuning. Yeah. Can you go back one slide? Go back. Here, for example, you see that when you add noise, your erasure noise is a big patch, right? It's a patch of what 10 by 10 pixels or something. I think even there you should just let the erasure be 1 pixel at a time. Otherwise, there is I think you need to tune it a little bit better. Yeah, I think you need to tune the augmentation better. Yeah, I think it's the random erasing is too large, and maybe the rotation is too extreme. Yeah, try to play around. You should gain accuracy from augmentation. Yeah, go ahead.
After we remove the combinations with too many augmentations, the rest of data is here. The most obvious part is at the bottom left corner with a knife missing its lower body. Okay?
Hey? What is the 9 missing?
Yes.
This one here. Yeah, you see that your random erasing patch is too big. Yeah, you see
yes,
that.
Maybe I have set the value too high. Okay.
Yeah, you can fix it. Yeah, no, it's not a big deal.
Okay, next page. This bar chart is much clearer. We found that random erasing is also affecting much performance. And next page. So after removing, this data should all be readable for us and the machine.
That's nice.
And so we set our epoch to 50, trying to obtain better module.
50, 50, not 15, right? 50.
Yes,
Right?
50.
Okay, go ahead. Are you pushing it too large? Okay. And still you have no advantage, right? Still you have no advantage.
Yes. Here we can see all the accuracy results are above 95%.
Wow.
And among these, the best performing module is adding none of the transforms.
Strange, yeah, it's strange. Because now you have tuned it well, right? Now you have tuned it correctly. The rotation is okay. You remove the erasure. Yeah, why there is no, yeah, very strange, very strange. Go ahead.
Any transform add to the module makes the performance worse, whether it's a little bit. After we add epoch, none of the transform is better than no augmentation. I originally thought that maybe the poor performance is because of the lack of epochs. And then we found that it has never been a problem.
Yeah, exactly. Because the learning problem is very stable. So yeah. Very strange. Very strange.
Next page. This is the QA for text 2. First, which augmentation gave the largest improvement? We got none of them improved the baseline accuracy. The result with no augmentation always has the highest accuracy. And the combination outperform single augmentations. Not at all. Specifically, elastic distortion perform worse than all other options. With the exception of elastic distortion, single augmentation generally perform better than their combinations. So, were there any augmentations that hurt performance? Yes, elastic distortion hurts a lot. Finally, did augmentation reduce overfitting? According to our results, it did not reduce overfitting significantly.
So you had a plot in your simulation. You had a plot of the accuracy on test and train set, and you see that the accuracy on train set keeps increasing. Is that what you're saying?
It is increasing, but not too.
Nice. Yeah, very strange. Very strange. We will see with the other groups what they say. I don't have an explanation for you. Because you applied the augmentation. So what percentage? Maybe that's the thing. So you apply data augmentation. So you apply data augmentation to all of the images that go into the model, right? And because you tuned it, right? Even your rotation is between -15 and +15. So everything is, because what I would have suggested you is to do this, right? So you start from a pre-trained network, right? And so you train it for, let's say, 10 epochs, because after 10 epochs, you already have 90%, right? And then you start from the network, and then you train it with the augmentation as a fine-tuning. And then you see if you can improve, let's say, between for the next 5 epochs, using only the dataset data or using only augmented data. And that should clarify. Because the only thing that I can imagine is that you augment too much, right? So your augmentation is very aggressive. So the network never really sees the original data. But you did a good job, right? You try to eliminate and to do this, and the ranges are all reasonable. So not sure. Let's see the other groups. Maybe we figure out what's the issue. I don't have a good guess now why you don't augment. Okay, go ahead, please. Go ahead.
Okay, then here's a part of task 3. Next page. We try to analyze the error rates for each classes. Then we use the best performing model from task 1, which have no augmentation, and we can see from this bar chart, the digit 3 is the one have the highest error rate. Okay, next page. And here's a confusion matrix, and we can see from the diagonal the correction rate is very high, but we can see like in the number 3 and number 4 for digit 3, it is usually misclassified to 5, as I circled here, and for digit 4 is usually get misclassified to 9. I think this basically they look kind of similar, so that's why they are the most confused for 3 and 4. So
you're 3 and 8 because the other group had a very large. Do you remember the other group had 3 and 8 as very easily confused digits, but not for your model.
Yeah, that's true, but I don't know. I think maybe so for our model 3 and 8 are fine.
Yeah. I mean, it's just an observation, right? We don't know where it comes from. Go ahead.
Okay. Next page. And then we do the data imbalance experiment. We set up our target class as the hardest class, which is the digit 3. So we reduce the proportion of the 3 in our training set, which is have four levels: 100%, 50%, 20%, and 10%. And let's see the result. Next page. Okay, as we can see from this chart, we reduced the proportion of 3 in our training set, and like 50%, the model is still performing fine, but in 20%, the accuracy rate just dropped, and for 10%, accuracy rate just dropped below 0.9. But it's still not very significantly like affect the overall performance, but it still have the drop, as we can see. Next page.
Very nice.
Okay, so next part is the task 4. Next page. We can take a look at how we generated the training pairs. And by the requirement of task 4, we implemented a custom class called MS pairs to handle the data generation logic. And for the initialization, we group all the data by their labels. And this creates a structure where we can easily access all the zeros and all the ones, and so on. And another aspect is class balancing. And to prevent the model from developing a bias, we ensure a 50 and 50 split between the positive and negative samples. And every time the get item is called, we split the virtual coin to decide if we're giving the model a matching pair or a non-matching pair. And for the positive pairs, where the target y equals 1, we pick one digit and then randomly select 2 different images of that same digit. And for negative pairs, where y equals 0, we select 2 different digits first and then take one representative image from each group. And when performing the preprocessing, we normalize the pixel values to 0 to 1 range and then flatten the images into the 7 184 dimensional vectors, and this makes them ready for our MLP-based embedding net and
let me correct you. Let me correct you. So you go from 2D images to one vector of 784 entries. It's not a 784 dimension tensor. Okay, so just a correction there. You know what it is, Emma? You understand what I mean, right? Yeah. You understand what I mean, right?
Yeah. Yes.
Just correct it. It's 1D vector of dimension 784. Go ahead.
Oh, okay. And this approach ensures that our network receive a diverse and balanced set.
Let me just understand this. So you have one network that generates two embedding, right? Is that correct? So the output is a triplet, right? The output of a network is a triplet, correct?
Yes.
And target? What is the value of? So what's the size of image one? What's the size of image two? And what is the size of target?
The size of image one. The size of image one is like just load the data set in the data.
This is no. So the size of image one is 784. Okay. Size of image two is also 784. Correct?
Yes.
And what is the size of target?
The size of target.
Yeah.
I think it's also 784.
And how do you compute the loss then? How do you compute the loss? Go ahead. How do you compute the loss?
I'm checking the code now.
I mean, it must be okay. That's it. You can also share the code if you want. I just don't understand.
Can I finish my presentation and then I can answer the question I want.
But I mean, can you please tell me how you compute the loss, right? So because I don't understand. So because your loss must be based on the label Y. Huh? So how from the label Y, how do you compute the loss?
I think we calculate like the distance between the embeddings.
So the embeddings, they are image one and image two, right? The embeddings will be image one and image two.
Yes.
And what is target then?
The target.
Like how does target enter into the loss?
I think by the label.
So target predicts if they are the same label or the different label?
Yes. like the target is 1 or the 1 and 0, like 1 represent
the same level
pairs
with
are
different.
like,
Yes.
and 0 is the difference.
And then you have cross entropy loss between the target and the label Y. And then you have the distance between the embedding if the label is 1, I guess, right? No, if the label is 0, right? Like, so if the label is 1, then they're the same image, then the distance doesn't matter. But if they are different, then the loss depends on the distance between the two embeddings. Is that correct?
Yes.
Okay, go ahead.
Next page, thank you. Okay. And the plot illustrates the training loss over 15 epochs using the control.
So here the embedding dimension is your is the size of image 1 and image 2, correct?
The dimension is yes.
Okay, go ahead. Good. Go ahead.
And we compare the embedding dimension 2 and 16. 2 in blue and 16 in orange. And both models converge smoothly, but there is a performance gap. The model with 16 dimension will achieve a lower loss and converge faster than the 2-dimensional. And because the higher dimensional embedding space allows the model to capture more features, so it leads to a better separation. And so, but the 2D embedding is somewhat limited in its representational power, resulting in a higher loss. Next page.
Oh, nice.
In this,
That's nice.
on the left, we have the 2-dimensional version. You can see the clusters forming, but they're somewhat crowded and overlapping. And that's also because the 2-dimensional isn't enough for the model to separate all the 10 digits perfectly. But when we look at the 16-dimension version visualized using TSNE, the difference is huge, and each digit is in its own clear with almost no overlap.
So your most confused digits were were not 3 and 8. Your most confused digits were 4 and 9, right? Correct?
What?
I said from your model, right? The most confused digits were 4 and 9, right? From the previous task. Can the guys from the
yes,
4 and 9? Okay.
Yeah, 4 and 9.
Let me see. The 4 is the gray. There are too many grays. Can you tell me what is the cluster for the 4? And can I see that the 9 is the cerulean, right? So you see that there is a chunk of blue in there, which makes sense. And then what is the red that goes there? It's the 3 that gets confused with the 9. Very good. Then the 3 with the 9. And I think that now the story changed a little bit, right? Also the 9 with the 4. Yeah. Nice. I think, yeah, nice. And what's stranded all along in the middle? It's the green, which is the 2, which is going toward the 7. Also good. Very nice. Go ahead. Very nice.
Next page. And finally, we move to the recovery test to see if our model truly learned the structure of the digit. And following the PDF, we ignore the pair labels and focus only on the output vector. And then we ran a K-means algorithm with K equals 10 on these embeddings to if they would actually group together. And by the plots, the result shows that the 16-dimensional embeddings were projected into 2 dimensions using TSNE, and the K-means algorithm successfully identified 10 distinct clusters.
Very good.
And our clustering.
You can tell the people what is NMI and why it matters. Yeah. Yeah, just tell people what is this purity. Yeah.
The purity is almost like 95%, and the cluster accuracy is 98%.
So the purity is here it's NMI is the mutual information. So it's the distribution of the labels inside each cluster. So the NMI will go to 1 if you only have 1 label in each cluster, right? So it's each cluster is pure in the sense that they only contain a distribution, which is that of the corresponding digits. Very nice, very nice, very nice. Okay, very good, nice, very good. Okay, any other comment? Any other? Okay, go ahead. Mm-hmm. Mm-hmm. Go ahead. Is there some other slides, guys? You guys are happy?
Okay, so these are the task force questions and answers. Yep. Okay, thank you. Guys. This is our presentation.
So you don't have a thank you slide? Okay, you don't have a closing slide? Next time put a closing slide so we know when you guys are done.
Okay. My fault.
No, just joking, of course. Very nice, very nice. Yeah, so this network here, you have a better performance than the other guys. I had a question for you, right? The question that I had is the following, okay? So now the network can take 2 pair of images, right? And it produces 2 embedding. My question is as follows. If you flip the order of the images, how different is the embedding? That's my question. Because the group before, they use the same network. If you use the same network, it means that they are order invariant, right? Because if you put image 1 and image 2, they go to the same network. And so the output is the same if you put image 1 and 2 or image 2 and 1, okay? But you guys have a network that can take the images with a certain order. So I wonder how symmetric is the output if you flip image 1 and image 2. Do you have an answer?
I think right now we don't have the answer.
Can you tell me next time? Because I suspect that what you can do is that you can do the augmentation, and when you put a pair as image 1, image 2, you also put a pair as image 2 and image 1, and then you can teach the network to be symmetric, right? Otherwise, the network, because the performance is very nice, so it must be symmetric, right? It must be symmetric. I just wonder if the network learns to be order invariant, right? Because usually it's tough to do a network which is order invariant, right? So if you have this type of networks, it's hard to teach them to be invariant to the order, and so people usually use some type of embedding which is order invariant, right? And yeah, I just wonder if the network learn to be order invariant. Okay, can you tell me next time? And please tell me, otherwise I forget, okay? Because there are many things in my life, and if I forget to ask you next time, please remind me to tell me. Okay, let's have a 3 minutes break. We just walk around, drink some water, get some more coffee if you want. I'll see you back at 38, okay? I'll just walk around a little bit, 3 minutes break, and then we'll come back. Ciao, guys. Okay, guys, let's go with the next group. Do we want to do group C or group D or group A? Guys, tell me. Yeah, go ahead, guys. Either group.
Maybe we can do group B first.
Okay, go ahead. Go ahead.
Can someone what do you call it, like screen share the presentation that is in my group?
Can you try to fix your microphone? It seems that you're talking to us from the depth of the sea. Try to fix it a little bit. I cannot
I'm in the
understand.
metro right now, so it's a bit hard, but I'll try my best to present there.
Okay, okay. Let's see. Go ahead, guys. And group D, please come ahead and tell us.
Oh, all right, thank you. I think the mic might be a little bit bad right now. I'm sorry for that. But I'll try my best to present here. So I start with the preliminary setup. So essentially, I looked at the tape, and then like 70,000 pictures, I think. And then we normalized them. So the pixel range was from 0 to 1 by dividing by 255. And then we split them up into the training set, the validation set, and the test set. Next slide, please. Yeah, and so the main objective of the task one was to essentially research the wide or like the different architectural families. So the first one was wide, and then deep, and then the bottleneck. And we had to test like different neuron budgets from 1,000 to 3,000 with like 200 steps or like steps of 200 essentially. And then for the optimizer and like the learning rate and the epochs, and that's like all the different variables. I chose like the smaller ones because it took a lot of time to train them. So that's why I chose like epochs 10, Lighter 128, and yeah, and then like 10 initialization because we needed that. Next slide, please. Yeah, so here looking at the different plots. This is the average plot or like the average accuracy for the different architectural families. So firstly, if we look at the wide family, it seems that around like 1,400 or somewhere like that is where the peak accuracy of it was. And I think like our plot is probably a lot more, how do you call it, like it goes up and down a lot more because I only have 10 epochs. It might be because of that or something else. I'm not entirely sure. But for the wide family, you can see that like with less than your own budget, you like well less and less, but like for the lower your own budget, it seems like it performed better. And then for the deep family.
At this averaged or not? They don't look average, right? Did you average across 10 ranks or not?
Yes. I
Really,
think I did.
they're so noisy, and they're so noisy, even when they are up because the range is so small, right? Because the range is so small. Yeah, just change the third digits. Okay, understand. So the pattern is basically flat, right? It's just if you had put them in the same plot, I think you would have seen that the wide one is basically flat. Go ahead.
Okay. Yeah, and then for the deep one, it seems like the more neuron budget we used, the better it got, like the accuracy. And then for the bottleneck, you see that it like improves, and then it gets really bumpy, which could be like because of the dimension reduction. So it's well put there. It can like affect the things.
But it's a third digits, right? So it's a change in the third digits. So so it's very okay. Go ahead.
But yeah, but overall, I think it was the wide that was the best performing from the you can see on the plots. And then next slide, please. Yeah, and then here for the overfitting and underfitting, it's a bit hard to tell because I didn't record the training and the test accuracy, so we can't really we can't be sure of that. But I think that based on what you can see, the smaller models are probably underfit because they're improving a lot, and also we're testing this against the validation set, right, which doesn't have anything with the training set to do. But yeah, then for the if you see the deep architecture there, the improvement is very small at the end, which could for the maximum, which could prove that it might be a bit overfit. But yeah.
Okay. Okay.
So now we're going to go with task 2, the data augmentation. So where we look at the data augmentation, the main goal here is to see if we could teach our neural network to generalize better by artificially expand our data set. The strict rule we follow was that this filter or distortion could only be applied to our training data, leaving the validation and test set completely untouched to ensure the fair evaluation.
Of course, of course.
So the baselines and the setup to keep our experiment scientifically valid, we had to lock in our architecture. We took the best performing model from task 1, which were the Y architecture with a 1,400 neuron hidden layer. Trained normally, then this gives us a solid baseline validation accuracy of 97.94%. We also wrote a custom dataset loader so that our image edits happen dynamically on the fly as the batch were loaded rather than saving thousands of new images to the disk.
Can you just a second? Tell me again the number of iteration and the batch size. What was that?
Can you ask again?
Can you tell me? Can you remind me the batch size and the number of iteration?
Here.
Batch size 128, iteration. No, definition is there. What is the epoch? 10 epochs. Okay, go ahead. Very good. 10 epochs. Good. Because the other group did 15. Okay, good. Go ahead.
So here, the techniques we implement 5 individual transformation. If you look at the grid, you can think of this like adjusting a camera lens or editing in the darkroom. We use geometric shift, like rotating the number up to 50 degrees, zooming in, zoom out, and panning them a few pixels. We also test occlusion and noise by adding a layer of Gaussian grain and randomly erasing chunk of the image. We test all 5 individually plus a few combination filter.
Very good.
So the result, here are the final validation result. As you can see from the table and the chart, the most effective augmentation was scaling, hitting the 98.18 accuracy, closely followed by the rotation. Interestingly, we found that random erasing actually hurt our performance significantly, dropping us well below the baseline. It turned out that stacking too many distortion, like combining rotation, noise, and erasing all at once, degrade the image way too much for the network to extract meaningful features, resulting in the worst performance overall.
Very nice. Very nice. Very nice.
So finally, we want to answer the core question: did this actually reduce overfitting? By plotting the gap between our training accuracy and validation accuracy, we can see exactly how the model behaved. Heavy distortion like random erasing and the combination filter shrank the train value gap the most. However, because the overall accuracy was so poor, they act as strong as the regularizers. The sweet spot was scaling and rotation, which gave us a slight improvement in the overfitting gap compared to the baseline, while actually boosting our overall accuracy. And that's wrap up task 2.
Just a second. Can you go? Sorry, can you go back one? Go back one slide, please. Oop. So here the baseline is at the middle, right? And then the accuracy, you have the improvement by rotation and scaling. Okay. And then the top one, you have validation accuracy, And where is the non? Non is 097. So you get to 0983 with rotation. And then the combination rotation, you don't have the combination rotation plus rotation plus translation. You don't have rotation plus scaling. Okay, no, it doesn't matter. Okay, good. Go to the next slide, please. Now here, overfitting gap by augmentation. Okay, because the overfitting gap is an absolute gap, is not a relative gap, right? Understood. So the overfitting gap goes, let me think of this. The overfitting gap, you take the distance, So you want the gap to be, just help me. Do you want the gap to be positive or negative? So you want the validation to be higher than the training. You want the test to be higher than the accuracy. So in that case, the gap is positive or negative?
The training to be have in the.
You understand my question, right? Is it test minus training, or is it training minus test?
Training minus test.
Training minus test. So we want the gap to be negative, right? So rotation plus translation is the best one.
Oh, I mean the opposite. Oh, I mean the opposite.
Okay, let's redo this. I get confused, okay? So the overfitting gap is test minus train, correct?
Yes.
Okay, so what we want is that we want the largest positive gap, correct?
Yes.
Do you want to check your answer? You don't seem too sure. You don't seem too sure, right? Because what you're saying, you see that what you're saying is the opposite of what we see, right? Because I mean, what you're saying is the opposite of what we want to see. Because we would want to see that if
you say.
Okay, so what you want to see is that when you add augmentation, right, you reduce the gap between training and test, right? But here, when you add augmentation, then you actually decrease the gap between train versus test, right? So which one is it?
I think it's the positive one.
So you're telling me that the baseline is the one where there is. So the baseline is the one where there is the most or the least overfitting?
The list?
Okay, so if baseline is that's the least overfitting, what is the formula that we are looking at? It's
this one.
It's good. Got it. Is it training minus test? Yeah, good. Is it training minus test? Good. Okay, we figured this out. Okay, very nice. Go ahead. Actually, go back one more. Sorry, I'm still looking at it. Because the noise, so the scaling and the noise, yeah. Because you understand the noise makes the dataset more robust, right? In the sense that when you are really using the model at inference, right, of course you're going to have some optical noise, right? But of course, since your test set is clean, you don't see the improvement of using this, right? So it's a good point, right? It's a good point. Yeah. Like if your camera gets dirty during inference, then you're going to have noise. But in the test set, you don't have this condition, so you don't notice the robustness that you gain with noise. That makes sense. Yeah, I just wish can you add for me translation plus rotation to the test? Because if you go back, your best combination was translation and rotation, right? Yeah, you see, rotation and scaling. Sorry, rotation and scaling. Rotation, and then you don't have rotation and scaling, right? You have rotation and translation. I would like just to see rotation and scaling. That's it.
Okay.
Yeah, that's it. Okay. Go ahead. Next task.
Next is task 3. Okay. This task has two main goals. The first goal is to analyze the model's performance for each digit class in order to identify which digits are hardest to classify and which mistake happen most often. And the second goal is to study how the models behave
when the training data becomes imbalanced, meaning that one class has fewer training samples than others. For this task, I kept the baseline model, big, small, test 1, and test 2. The baseline architecture is from the white family, which hidden size is 1,400. The model was trained for 10 epochs, with seed equal 42, and the dataset split was 40% training, 10% validation, and 20% test. By keeping the model fixed, we focus on understanding the error patterns and effect of data imbalance instead of mixing in changes caused by different architectures. Now I will first show the baseline model's class-wise performance. Next page. This slide shows that the per-class accuracy and per-class error rate of the baseline model on the test set. From the accuracy plot on the left, we can see that the model does not perform equally well on all digit classes, even though the overall accuracy is high. Some digits are clearly more difficult than others. In this experiment, the hardest digit is 3, and the next relative difficult digits are 4 and 9. The error rate plot on the right shows the same pattern. Digit 3 has the highest error rate, which means the model takes mistakes on this class more often than on others. The key message of this slide is that the high overall accuracy does not mean that every class performs equally well. If we only look at the overall accuracy, we may miss the fact that some classes are already much weaker than others. So to understand where the model fails, we next look at the confusion matrix. Okay, next page. This slide presents the confusion matrix of the baseline model on test set. The diagonal entries represent correct predictions, so darker value along the diagonal are better. The off-diagonal entries show misclassifications, meaning how often one digit is predicted as another digit. We can see that most samples are classified correctly because the diagonal is very strong. However, the mistakes are not separate randomly. Instead, they are concentrated on a few pairs of visually similar digits. This means that the model is not simply making random errors. It tends to confuse digits that already look similar in handwritten form. So the confusion matrix helps us see where the model fails, not just how much it fails. Next, I will show the most frequent mistake pairs and some actual misclassified examples. Next slide.
Misclassification example.
This slide summarizes the most frequent mistake pairs and also show real examples of misclassified images. In this experiment, the most common mistakes are 4 predict as 9, which happened 21 times, and 3 predict as 5, which happened 19 times, and 3 predict as 8, which happened 14 times, and 9 predict as 4, which happened 9 times. These mistakes are quite reasonable because these digit pairs are visually similar in handwritten form. For example, 4 and 9 look similar when the handwritten 4 has more closed up shape. Likewise, 3 and 5 both contain upper and lower curves, so if the middle structure is unclear, they can easily be confused. Also, 3 and 8 may look similar when the two arcs of the handwritten 3 appear almost closed. So the main message.
I just want to say, you see in the first row, there is what I was telling you guys, that in the West, right? We have different ways of writing the 4. So you see that you can write the 4 either with an open top, like in your first element in the first row, or you can do it with the diagonal loop, which is the first row, third column. So when you are little, like we're not like in Taiwan that they tell us how to write numbers. Right? So different people have different preferences on how to write the numbers. And if you see it also for the 7, so the 7, sometimes I was saying, sometimes we put the little dash in the middle or not. So the model, of course, gets more confused because he has to learn that there are 2 ways of writing the same number, right? So it's a harder class in that sense. Go ahead.
Okay.
Did I confuse you? Sorry, I didn't want to interrupt you. Yeah.
Okay. Since digit 3 is the hardest class in this baseline analysis, so I will use it as a target class in advanced experiments. So next slide. This slide explains the design of the imbalanced experiment. Since digit 3 is the hardest class in the baseline analysis, I selected it as the effect class. Then I create 3 imbalanced scenarios for 50%, 20%, and 10%. This means that I progressively reduce the number of training samples for digit 3 while keeping other classes unchanged. So the validation set and test set remain unchanged, so the comparison across imbalance levels stay fair. Also, in this experiment, I use the baseline as the 100% reference instead of retraining a new one. So this can avoid extra variations caused by reshuffling of the full training set. I just retrain the one, but the correct rate is not the same. So I use the set.
It's a good point. That's why you want to fix the randomness, right? So that then you can, as you said, you can repeat the shuffling of the data. Yeah, it's a good point. It's a good point.
Yes.
Go ahead.
The table below summarizes the overall test accuracy, digit 3 accuracy, digit 3 error rate, and the number of training samples under each imbalance level. Now I will show how the accuracy changes as the training data for digit 3 decreases. Next page. This slide shows the effect of class imbalance on model performance. The plot on the top right shows the accuracy of all digit classes under different imbalance levels. Most classes remain relatively stable, but the effect class digit 3 drop much more clearly than others. A similar plot on the bottom left compares digit 3 accuracy with overall accuracy. Here we can clearly see that as the training data for digit 3 is reduced from 100% to 50%, 20%, and 10%, the accuracy of digit 3 increases progressively. However, the overall accuracy decreased much less. This tells us something important, just like aggregate accuracy can hide class-specific failures. In other words, the model may still look strong if we only look at overall accuracy, but one specific class may already be significantly degraded because it has too little training data. Okay, next slide.
Okay, let's hear this one.
Can you hear it?
Yeah, we can hear you.
Okay. Here's my task. Let me see where to do the data pairing and constructive loss.
Can you repeat? How do you pronounce this? Can you repeat the name of the network?
The Siamese.
Siamese.
Oh, Siamese. Oh, Siamese
Wait,
network.
wait.
Siamese.
Tell me. Okay, I'll just torture you, right? Do you know why this network is called in this way? It's a very racist. I'll tell you something. It's a very racist reason.
Oh, okay, I will search that later.
No. Let's discuss it now. Come on. We have been, we have to. The focus is very fragile, right? So if we discuss a little bit, then you relax, and then there is everybody has a moment to breathe, so we can focus on what you're gonna call or do next. So this is called Siamese network. And what does the Siamese come from?
Kind of some kind of population.
Siam. It's like the country of Siam, and the country of Siam was the old name for which country today? Thailand. Very good. Very good. Oh. And so why do you think, what does Thailand have to do with this network in your mind? It's a very racist reason, okay? Because there is a very sad illness where two kids are born with some parts of their body which is shared, and the disease is called the Siamese twins.
Oh, okay, I see.
So the Siamese twins is when it's very unfortunate, right? The Siamese twins is the unfortunate illness. We don't want to discuss it more, as I very sad. When two kids are born with some shared part of their body. But why is the illness called the illness of Thailand? Because the first recorded case in history of Siamese twins was from Thailand.
Okay. Interesting.
Because right now they call these people that have this disease, they call them conjoined twins. So it's less, it's less racist. There's no other way to say it. It's less racist. And so, but instead of calling it like the conjoined network, they still call it the Siamese network. So, and it's the other way that we use the adjective Siamese, which again, it's kind of racist because there is a country and white people decided to call it Siam, even if themselves they want to call it Thailand, right? So it's not nice. But we say the Siamese cat. Do you know which one is the Siamese cat?
Yeah, I know the Siamese cat looked like.
Okay, so it's like for Taiwanese we have something similar, right? For example, they call it like the Formosan bear, right? The bear in Taiwan, they call it the Formosan bear. But we didn't choose, the Taiwanese people didn't choose to call themselves Formosa, right? So the white people, they came to invade the country, and they called the country Formosa. So, you know what I mean? It's kind of like, it's not nice, right? The people still use an adjective that was given to the place, but it was chosen by some invaders, right? Some occupiers, some people that came for, it reflects the point of view of the language, and the point of view of the language is the European-centric point of view of the language, right? So it's something that we have to, it's something that it's something that is not particularly sensitive. Does it make sense? Does it make sense?
No.
No.
Oh, it makes sense.
Like when you see that people use the adjective Formosa instead of saying Taiwan, do you feel like it's, how do you feel about it?
Formosa means a beautiful place, right? So I think, the Taiwan is a beautiful place.
I see. So for you, it's not a problem because they don't call a terrible illness Formosan twins or something, right? But if it was, instead of being Siamese twins, was Formosan twins, how would you feel about it?
Well, it sounds more sounds way better after I realized, after I know that 7 means mean. Yeah.
Yeah. That's my point. Okay, go ahead, guys. Again, just something to discuss, something different. Otherwise, we go crazy. Go ahead.
So my part is to do the Siamese network to do data pairing and contrastive loss. First, we need to design a network that take pairs of images and output embedding vectors, and using binary information to classify the data into a different category, and implement the Euclidean distance that put the same digits together and push the different digits apart. Okay, next. And next page, yeah. And first, let's see how the networks works. And let's see networks will embedding the images into the vectors and label them into 1 and 0. 1 means 1 stands positive pairs, which means the same, and the 0 means the negative pairs, which is different, and calculate the distance, process the loss function. And here's the step that how to train the models. First, to download the MNIST data set for pairing, and pairing up the data and labeling, and build a loop that make the model learning how to classify the category. Okay, next page. And here's the loss function and the merge. And in the loss function, the d means the distance, and the m means the merge. The merge is define the median distance that must be remained between the different categories. And
so we call it margin. The pronunciation is margin. Okay.
Yeah. Okay. March. Okay. When the model margin.
You have to pronounce the end.
Margin. Okay. When the model identifies
I'm not
images,
criticizing you. Okay. I'm just trying to help you with the pronunciation. Okay.
Yeah. The pronunciation. Yeah. Pronunciation is important. I know. Yeah.
No, because the way Taiwanese students study English, it's with a lot of listening and not so much of talking, right? So we just want to help you guys there.
Yeah, I know.
Go ahead.
When the models identify the images are the same, it will label one. It will label the y is 1. Otherwise, the y will be 0. And for the minutes, and when the y is 1, for the minutes L, the distance square must be close to 0. So it will put the same together. And when the y is 0, the function left to least, and we can see if the distance is greater than the merge, it means that the distance is already large enough, so the loss is 0. And if the distance is less than the merging, the loss will be very large to force the models push the difference apart until the distance is greater than merging. Yeah. Next is next page, please. And next page, and this page shows that how the merges affect the result. And the reason I chose 2 and 7 for identifying, because their skeletal structure is highly similar in handwriting. They both have the horizontal strike, create a common visual anchor, and in topological ways that they can confuse the model easily. So make the model focus on the detail to identify the patches difference, not only on the bold shapes. And next. Next page, please. And here's the chart of the result. And you can see the red dot is above the threshold, and the blue dot is below the threshold. And
so you're tuning the threshold. Okay, go ahead.
Okay. The merging is bit greater than 6, especially 8 and 9. We can see the distance is way better than the threshold. That shows the model can identify the images difference clearly. And when the merging is less than 5, and we can see the distance is under the threshold, shows that at least kind of merging, the model can not really identify the difference between 2 and 7. And here's the exception in margin number 7. Although it's greater than 6, but the distance is still less than 1.5. Why? Here's some reasons. Because the model training is nonlinear converge, so it may happen gradient oscillation that cause the models can reach our target. And when the model's initialization and the batching is random, so the random batching and initialization cause the temporary performance dips, so that cause the merging equals 7 is less than 1.5. Yeah, which is not which is not like usually. And next is our conclusion. Next, please. Next page. Yeah. And here's our conclusion. The network will embed our images into vector and use the vector to process the loss function to see they're same or different. And choosing the structure similar digits can help you get a better training results. And choose the suitable mergings can make the models identify the images more properly. And yes, my part is over. And next page.
No. What about the k-means? Did you do the k-means?
Okay. Well, what the k-means?
Yeah. Okay, good. Okay. Got it. Because it was a conclusion. I was like, oh, what is the rest? Okay, go ahead.
Everybody hear me?
Yes.
Hello everyone. Today I will be presenting an experiment that explores how mapping data to embedding spaces of different dimensions impacts clustering performance. Next page, please. Okay. So we will compare two models, one with 2 dimensions and one with 60 dimensions. So see that the higher dimensional features yield significant improvements. Next page. Next page, please. Okay. So first, let's look at the training loss over 10 epochs. Both models converge successfully. However, it's clear that the 16-dimensional model not only started with a lower loss, but also converged to the much better final result. This indicates that the higher dimensional space provides a better feature capturing capabilities for optimizations. Next page, please. So this slide shows the results for G equals 2. Since the dimensionality is exactly 2, we can plot the latent space directly on the 2D plane. As you can see, the model performs exceptionally well, achieving 0.9970 in both purity and accuracy. The different digit classes are already clearly separated. Next page, please. And then we examine the D equals 60 model. If the accuracy reaches a near perfect 0.9998, because we cannot plot 16 dimensions directly, we use the TSNB algorithm to reduce it to 2D for visualization. Compared to the previous slide, you can noticeably see that each cluster is much tighter, and the distances or margins between different classes have been pulled further apart. Next page. To summarize the differences, I put together this comparison table, while the 2D model is already very impressive. The 16D model outperforms across all metrics. The reason is that higher dimensions bring the neural network at larger representation space. The model doesn't have to squeeze data points into a crowded low-dimensional area, allowing it to easily separate complex features. Next page. So finally, to conclude our experience, we covered that increasing
embedding the dimensional is perfect feature separation and model robustness. However, the fact that D equals to achieve 99.7% accuracy tells us that the inherent features of these data sets are already quite distinct. For future machine learning projects, we can balance computational resources and accuracy requirements when choosing the appropriate dimensional. This concludes my presentation.
So this accuracy is the k-means accuracy, right? Is the accuracy after k-means, correct? It's not the accuracy of the Siamese network.
Yeah.
So do you have the number for the baseline k-means without the features?
Maybe.
Yeah, just study next time. So it's the same comment as the other group, right? Because you could also do k-means on the original images, and you can show that the performance of k-means is, let's say, 20% below this accuracy, right? So you can say, oh, if I do k-means on the original space, I get an accuracy of like 70%. If I do k-means on the embedding space, I get an accuracy of 99%. So this is, so you get a sense of how much the embedding help you do in the clustering, okay?
Okay.
Make sense?
Makes sense.
Very good. Do you have a movie presentation today, guys? Otherwise, I think well, the other two groups, we do them next time, if it's okay with you. Because as always, you see, he said, thank you for your time and attention, right? So the attention is the scarce resource. I cannot pay attention to the presentation for more than 2 hours at a time. So if we have a movie presentation, we do the movie presentation. Otherwise, we have a movie presentation next time. And the other two groups, we do the next week, please, guys, if it's okay with you. Otherwise, my attention level will decrease and I cannot be very present. Okay, is that okay with everybody? Do you have a movie presentation this week? No. We're going to have one next week, I think. Okay, very good, guys. So let me stop the recording. We say hi to the people over YouTube. Ciao, guys. And then, yeah.